is the second video for section 10.4 where we were working on differentiating the sine of x squared, but doing it with the power series rather than our normal differentiation formulas. So we wrote out all of the terms of the sine of x by substituting in the x squared piece that we need, and we came up with this power series here, or this Maclaurin series that we're going to turn into a power series. So what we need to do is come up with an expression that represents these powers, 6, 10, and 14. So without overthinking it, you can just go back to the sine of x formula here, and you can replace x with x squared. So if you take x squared and raise it to the 2k plus 1 power, you're going to get the 4k plus 2 power. So x to the 4k plus 2. And then in the denominator, you'll see that our factorial constants here haven't changed, so that will still be 2k plus 1 to the factorial. Or not to the factorial, but just factorial. So here we have a representation of the sine of x squared given its Maclaurin polynomial and the power series that represents that. So what we want to do is we want to take the derivative of the sine of x squared. And again, we can do it by taking the derivative of every single term and then trying to come up with a summation notation to represent that, or we can just take the derivative of the summation piece. So if we take a look at the derivative here of the power series from k equals 0 to infinity, negative 1 to the k times x to the 4k plus 2, all divided by 2k plus 1 factorial. We will work on getting the derivative that way. Okay, so one of the things that I'm going to do, again, is I'm going to remember that I have some constant multipliers, and I'm going to pull those out. I'm going to pull them out in front of my derivative. So 1 over 2k plus 1 factorial is a constant multiple. Okay, the only term that actually has any variables in it is x to the 4k plus 2. So I'm going to pull that out. And then I'm also going to pull out my negative 1 to the k, because that is also a constant. It alternates between plus and minus 1, but still a constant. So what I'm finding the derivative of here is x to the 4k plus 2. And again, we can just use a very simple power rule to find that derivative. So I'll have 4k plus 2 times x, and then I'll subtract the power by 1, which will give me 4k plus 1. So let's put this all together, and let's try to simplify what we have. So we'll have negative 1 to the k times 4k plus 2 times x to the 4k plus 1, all divided by 2k plus 1 factorial. Okay, so again, we want to see if we can simplify this. And what I'm looking at here is there any way that I can reduce these two terms? And at the moment, it doesn't really look like it, but if I factor out a 2 here in this top expression, I'll get 2 times 2k plus 1. Now, the 2k plus 1 here is going to be the first term in the factorial down here, and those two are going to cancel out, which leaves me with 2k plus 1 minus 1, or just 2k factorial in my denominator. let me put it all together in a summation. So I've got negative 1 to the k times, times 2. This 2 right here did not cancel out, so times 2 times x to the 4k plus 1 over 2k factorial. Alright, so this is the derivative of my power series for the sine of x squared. So then the question is, which commonly known function is this series a representative of? And if we just go back and take the derivative of the sine of x squared, we'd get the cosine of x squared times 2x using the chain rule. So that means that this power series here that we've written must represent that function, 2x cosine of x squared. Okay, so let's also find the radius and interval of convergence for this, since that may be something that we're asked to do as well. So remember, if we're finding the interval of convergence, that we're using the ratio or the root test on the absolute value of our power series. And so to do that, I'm going to do the limit as k approaches infinity, and I'm going to do a ratio test as opposed to a root test. I'm going to ignore my alternating signs, okay, because we're looking at the absolute value. So it'll be the absolute value of 2 times x to the 4 times k plus 1 power over 2 times k plus 1 quantity factorial. And then I'm going to divide by a sub k, or multiply by its reciprocal. So I'm going to go right to multiplying by the reciprocal, which would be 2k factorial over 2 times x to the 4k plus 1. And again, I want to simplify all of this to complete my ratio test by finding the limit, and then I can write the interval of convergence. So since that is something that we studied in section 9.2, you should already be familiar with doing some of this work. Might be a good time to pause the video, try to continue this on your own, and then we can come back together and check to make sure you have the correct interval of convergence. Now that you've paused and taken a minute to complete this ratio test, let's go ahead and talk about what the correct interval of convergence is. So as I take all of this and I line up some of the like terms here, the 2x raised to the 4k plus 2 over 2x to the 4k plus 1, everything's essentially going to cancel or reduce here except for an x to the first in the absolute value form. So you can see over here that I've pulled that outside of the limit. And then as far as our k factorials go, this is 2k plus 2 times 2k plus 1 times 2k times everything that comes after. So the 2k factorial will completely cancel within this factorial, leaving you with only 2k plus 2 times 2k plus 1. If you find the limit of this expression as k goes to infinity, the denominator will go to infinity while the top remains constant, meaning that the entire thing is going to go to 0. So I'm left with the expression, the absolute value of x times 0. And again, going back to the ratio test, when does the ratio test tell us that we converge? Well, it converges when our limit is between 0 and 1, including 0. And so the question is, for what value of x will this expression equal 0? And the answer is any value of x. You'll always be equal to 0, since 0 times x is always 0. Our interval of convergence then is negative infinity to infinity. So we did a lot of work within this problem. Let's just review. We started off with the function the sine of x squared, and we wanted to write its power series. So we could take the time to do what we learned in the last section and actually find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and we could write out all of the non-zero terms and create the Maclaurin series. But instead we used the given sine of x series, and we just squared each x to come up with a new series for sine of x squared. We then took the derivative of the summation, and we wrote the summation form of the derivative for the sine of x squared, and then we also noted what function that power series would represent by taking the derivative of the sine of x squared. We then continued to use the power series that was differentiated to find the interval of convergence. So that is the basic idea of what you're going to need to do in this section. So again, another option would be to take each term in the Maclaurin series and find its derivative, and then try to come up with a power series formula that would be representative of that derivative. So that's perfectly acceptable as well.